So in this lecture, we are going to look at Euler's formula for the pin-ended columns, and the reason why it is necessary is because see the earlier formula we derived where using the rigid bar and the rotational spring, that is analogically similar to understand, but it is not an exact formulation which you have over here. So the exact formulation was actually, and from the name itself, as you can say that it is the Euler's formula. It was given by Euler in the year 1757. Now, Euler, as you know, he was a polymath and he has these immense contributions in different fields of science and engineering, which is over there. And in fact, you will see the Euler's formula for the pin-ended columns, which we are going to derive, which he derived back then in 1757. That sort of got untested for several years till you essentially had experimental facilities. For example, now the short video experiment we saw, or when you can come to your labs and you can see the experimental tests on columns that you will do, and the critical load where the column starts to buckle, right, or the column snaps, right? You will see that load gives results which are very, very close to what Euler had derived way back in the 1757. And he was such a popular polymath back in his day. So I really like this quote, so I wanted to share with you. It was said by Pierre Simon Laplace that of Laplace transforms, that famous mathematician. He said that read Euler, he's the master of us all, right? So with that short phrase that we see over here, we'll go ahead and derive the formula for the pin-ended columns. And you will see that different books treat pin-ended columns, or not treat, represent pin-ended columns differently. So don't be confused if you're reading from one book or another. You will see that some books represent pin-ended columns like this, and some books like this. It is essentially the same thing. You are just having a column with a pin end at one corner and a roller end at the other. You have to have a roller, otherwise this point B will never go down. So this roller is represented in some books like this, and some books like this over here, the two rollers on the side. So you see, since it's pin-ended over here, this allows rotation over here, and this will also allow rotation over here once you push the load beyond a particular limit. And also the bending moments at here and here will be zero. So essentially the same thing. It is just which book you are referring to over here. Now if you take a look at this one, if this is how the overall buckling happens. So if you keep on increasing the load over here beyond a particular point, you will have this is the deflected shape of the column. And say if you have the y-axis and the x-axis marked over here, and say at a certain portion you have a deflection y, we're going to take a free body diagram and take a look at that. So let's go ahead and take a look at how Euler back in the day derived the famous formula for establishing the critical load for the pin-ended columns. So now we are going to derive the buckling formula for pin-ended columns. So pin columns, we are going to start with the pin columns, and later we'll move on to other support conditions, because this is the classic Euler column. This is the column which Euler started with, but the both ends are pin. Now if you see this one, you're applying a load P, you have a roller over here, and then this thing starts to buckle, something like this over here, and this is your y-axis and the x-axis, and at a certain distance x, you maybe have this deflection or the deformation y over here. Now as you can tell why this chapter on column is the last chapter, because this is essentially relates to deflection of beams. So if you see this one, columns or beams can be used interchangeably whether you're looking at horizontal or vertical members. So this essentially goes back to some of the basic concepts of the deflection of beams. For example, if you take a section of this beam over here, so let's say if I cut this beam somewhere about this particular section, and you draw the free body diagram of this one. So you have a load P from the top over here, and corresponding to that you will have a vertical reaction P as well, and this is the moment M at that particular section. The shear is not drawn in this particular case because there is no horizontal loading along the y-axis over here. So if you sort of try to write the expression for the M over here, as you can tell at the center point the deflection is y, so your M becomes equals to minus p times y. So your M becomes equals to minus p times y. Right? So now we know that our basic bending formula, that basic deflection formula, that is EI d square y by dx square equals to M that you have. So let's go ahead and write that at that particular section and see what we arrive at. So we arrive at this particular equation. Now if I take this term over here, p divided by ei, and say represent it with something else, say p square. So let's see if it's small p square. Let's see what we get. See this equation that we looked at, and let me mark it with this equation A right over here. Now does this particularly remind you of something? Yes, so this particular equation that you are looking at, it is a second order linear homogeneous differential equation that we have over here, and with also constant coefficients, right? So if you, how do we solve this equation? You are already familiar with that. You have a general solution for this one. So let's go ahead and write the general solution for this one. What we get is, so this is the general equation of this linear second order differential equation with constant coefficients. Now how do we sort of try to attempt and get the constants which are there? How did we do it for the beams? Yes, the same thing. We are going to use the boundary conditions. So let me go ahead and write the boundary conditions that we have. So we get, after substituting the boundary conditions, these things, that is C2 equals to 0 and C1 sine of PL equals to 0. Now if you take a look at this equation, the conditions are, so either C1 is 0 or sine of PL equals to 0 over here. Well, the condition of of C1 equals to 0 essentially would mean y equals to 0. So that means that your column is always straight. There is no deflection. So that becomes a trivial solution. So let's make a note of that, and we are going to equate sine PL equals to 0 over here. So we get, after substituting the boundary conditions, these things, that is C2 equals to 0 and C1 sine of PL equals to 0. Now if you take a look at this equation, the conditions are, so either C1 is 0 or sine of PL equals to 0 over here. Well, the condition of C1 equals to 0 essentially would mean y equals to 0. So that means that your column is always straight. There is no deflection. So that becomes a trivial solution. So let's make a note of that, and we are going to equate sine PL equals to 0 over here. So sine PL equals to 0 means your P must be equals to n pi. So there, where n is 1, 2, 3 and so on. So let's go ahead and write that, and then substitutes this small p. Remember, the small p which we have taken, the small p square, is p divided by ei. Eventually we are trying to get this p over here. So let's back substitute and see what we get over here. So we get this capital P as n square pi square ei by L square. Now remember, this is also for your values of n as 1, 2, 3, right, and so on and so forth. And this equation is important, so I'm going to go ahead and sort of put a box around that one over here. And also, if you put p equals to n pi by L over in this equation over here, what you will get the value of y. So if I put this small p equals to n pi by L, I will get the value of y as, so this is also an important equation which helps you give the deflected shape over here. Now remember one thing, that only when p takes these values, that p is This part is constant, pi square ei divided by L square. So only when n equals to 1 and p takes that particular value, you will get a corresponding deflected shape with n equals to 1 over here. When you take n equals to 2 over here, let me write this 2 a bit more clearly. So only when you take n equals to 2, you will get a corresponding deflected shape over here. So these are interdependent. So only when p takes these different values that you have over here, you will get a corresponding deflected shape, which is something like this over here. Now this term n over here, this represents this also, this is also known as the mode shapes. And how do these mode shapes look like? For example, if you substitute n over here and if you try to draw the configuration of the column, this is sort of how it looks like. So if the initial, say let's say for n equals to 1, if this was the initial configuration of the column, then when n is equal to 1, the deflected shape of the column looks something like this over here, right? Now let's say that when n equals to 2, then the deflected shape of the column would be something like this. Right, so these are called the mode shapes. So n represents the mode shape. So let's make a quick note of that as well. It is not particularly important, at least at this stage, but it is good to know. Now, can you think that whether n equals to 2 is logically feasible or not? Right, so let me write this first. N represents the mode shape. So if you think about it, that before the column reaches, before you have this n equals to 2 over here, at n equals to 1, the column has already buckled, right? So it is physically it is not possible to have n equals to 2. So that is why the critical load in the column happens when, that is p equals to pcr, happens when n equals to 1, for which the Euler's formula boils down to, for the pin-ended columns, it boils down to pcr equals to pi square ei divided by L square. So let's make a quick note of that one. Right, and the corresponding deflected shape is is going to be something like this. So for example, here if you have a pin at both the ends, suppose I had a pin over here with a roller and I had a pin over here is fixed to the base. So we have a pin and a roller kind of configuration. The deformed configuration becomes equals to, when n equals to 1, because this is the only practical case, this deformed configuration becomes c1 sine pi x by l. So let's make a note of that as well. So these are the two important relationships which Euler essentially derived when he was working on the formulation for the buckling of the pin-ended columns over there. So let's go back to the lecture and see that, just to try to summarize that what we learned in this one on how to derive the critical load and what are the consequences of that one. This is what we looked at in our derivation of the formula, that the general equation for the critical load is n square pi square ei divided by L square, and this is the equation for the deflected shape. Now, as we discussed, that this only when this p has these values given by these different ends, you will have the column, the bent shape of the column will be the one followed by this equation p that you have over here. And different values of n leads to different mode shapes. That also is something which we saw, but out of them only n is 1 is practical, because the column will already buckle before it reaches n equals to 2. Now this is the overall summary when n equals to 1 over here. For example, what we looked at was the Euler buckling load, that when n equals to 1 becomes pi square ei divided by L square. So this is something which should be ingrained in your memory, because you will see soon that for other support conditions they also rely on this particular formula. So this formula should be crystal clear in your head, that the critical load PCR is pi square ei divided by L square, and the deflected shape is something like this. Now it is very important and interesting to note that you see this constant c1 always is undetermined over here. So it's also because of this phenomena of the buckling that you have, this c1 remains undetermined, but this is the overall equation for the buckled shape that you have within the beam over here. Now that we have derived the one for the pin-ended columns, we are going to move ahead. That of course Euler did not stop with just deriving the equation for the pin-ended columns. He looked at other kind of support conditions as well. So let's go ahead and take a look, and for all of these, like the equations that we derived, we can derive the equations for those, but there is a simpler way to do that. Let's go ahead and take a look for other support conditions. How does this P critical or this PCR, how does it change depending upon the support conditions of the column?